This is Lecture 7, F for Calculus 2. It is on the preliminaries for numerical integration. Integration is much more difficult than differentiation. In fact, the majority of integrals do not have what are called closed-form solutions. Now, closed-form solution is a solution you would like to get. It is just a combination of all the functions we're familiar with: logarithms, exponents, polynomials, trig hyperbolic functions, all these combined using elementary operations that we're very used to, such as addition and subtraction. For example, the following would be a closed form solution if I said sine squared of x divided by 3x cubed minus e to the negative x squared. Say that's my solution. That is a closed form solution. Why do we like these? We like them because we understand them. We know what a sine wave is like. We know how a polynomial behaves. We know how a decaying exponential behaves. We understand a rational function. So by having these functions, not only are they easier to evaluate, but also they give us insight to the solution as a whole. But many times we don't get this. This is the goal, but it's not always achieved. Sometimes, though, the integral will look difficult, but it still has a closed form solution. Many of these have already been worked out. You can try to work them out yourself, or you can do what many people do, and that's go look up in a table of integrals. The table of integrals in the back of the textbook is fairly short, but you can see there's many integrals listed there. You can also get books from the library, and Abramovich and Stegen and some of these others that have many integrals listed, and you have a good chance of finding the one you're looking for if it does exist. People have been working these out for many years. You can also try the commercial computer solvers such as Mathematica. They will also give you closed form solutions, although they can look complicated, and sometimes different programs will give you different solutions, different closed form solutions, but you can use identities and show that they're similar. At any rate, that's one way to get it if you have a difficult integral. But now for those for which there are no solutions, you still can integrate. And what we're talking about here is not the indefinite integral. We then move to a definite integral. We're integrating from some limits a to b of some function f of x dx. Okay. Now, so this is one reason you would go to this numerical integration, is because you do not have a closed form solution. But there's another reason. Sometimes in design you will use numerical integration. Well, sometimes you might have a closed form solution. If you want to do a parameter study, sometimes some parameters, some set of functions will give you a closed form solution, but if you want to modify them, say you're making a bridge and you want to change the shape of things, the next shape or the next modification might not have a closed form solution. So design often relies on numerical integration, and in that case you can input a set of parameters and see a consistent set of results. For these integrals that do not have closed form solutions, there is something similar to that table of integrals, and that is special functions. Some definite integrals are so common and they appear so much. For example, the exponential that appears in statistics, or some other very commonly occurring functions. These have been worked out, and their values have been compiled and stored, and they've been given special names. Two very famous names are listed here. One's whoa, that was supposed to be the highlighter. The error function. Another are Bessel functions. We'll see some Bessel functions later on in the semester. They occur in mechanical engineering and physics, and studying, for example, heat distribution or stresses in a two-dimensional plate. Okay, so you will encounter these in physics. They've been studied, and then after they've given them the names, and then they start studying the behavior of these functions, they find that they are subject to special rules and special identities. For comparison, you can think of the logarithm function. The log is just a list of values. They were developed from looking at the inverse of exponentiation, not from any mechanical process or any arithmetic process. So a log is just a list of values. They're conveniently stored in your calculator, but they're still just a list of values, just like the results of the error function and the Bessel function are. But log has special name, and it has special identities and special rules. So we're not talking about these functions. Instead, we're talking about actual numerical integration that you would do on a computer. There are many methods of numerical integration. We're going to study 5 of them, and they're listed here. The right and left midpoint rule, this is just Riemann integration, the trapezoid rule, and then Simpson's rule. Again, all of them are methods to approximate, this pen does not switch, there we go, methods to approximate the definite integral. For this class, we are going to assume that the integrand, the f of x that is being integrated, is a continuous function. When you take courses in numerical methods, you will study how to handle functions that are discontinuous. But for right now, we just want to learn the method. So f is going to be a continuous function. In all these methods, we take the interval AB, which is the interval, an interval on the x-axis, and we subdivide it. We mesh it, right? Previously, we called the width of each mesh delta x. In numerical work, we tend to call that h. H is the same as delta x, and it is equal to b minus a, the endpoints, difference in the endpoints, divided by n, where n is the number of meshes. All these meshes will be uniform. Again, when you take courses in numerical methods, you will find how to adapt your mesh to the particular function. But for now, the mesh will be uniform. Counting is a problem. In fact, it has a name. It's called the Fencepost Problem. And here's what the Fencepost Problem is. If you have a group of fences here, so I set 6 fences, and let me just string some wire between them, create a fence. I have 6 posts, 6 fence posts, but the number of spaces between the fence posts is only 5. That might seem very elementary, but this does cause problems. If this fence situation is really a mesh, and you are studying some property in which you're looking at the interior points of the mesh, then when you go and in your computer program loop over all the meshes, you better only count to 5. If you count out here to 6, you're out here trying to find a property in an area where there is nothing, no material. On the other hand, if you are looking to match boundary conditions between each mesh, the conditions right here on these boundaries, if you don't count all the way to 6, then you'll miss the endpoint. This has applications to hydrocodes for those of you who are going into physics and more mechanical engineering, and also in electrical engineering as well. So this is a fence post counting problem. We have to pay attention to whether we're evaluating something on the interior or on the edges. Now you minimize your fence post problem by being very consistent in your notation. So here is what I do. This is what I use in practice, and it's what I encourage. The book does something different, right? I use capital N for the number of meshes. Then I use lowercase n for the counter. So in the case above, n is 5. And little n equal to 3 means this particular mesh right here. Okay. Now, the fence posts are really values of x, because this is the x-axis in our one-dimensional problems. Here's the y-axis. This pen doesn't work so well anymore. All right, so I'm going to start counting the meshes by 1. So the first mesh is mesh number 1. All right, but I'm going to flank it by x0 and x1. So now the values of the x on the sides of mesh 2 are x1 and x2. It just keeps going like this. This is x3. x4 lies between x3 and x4. x5 lies between x4 and x5. So I start the counter for the x's at 0 and go to n. That gives me n plus 1, capital N plus 1 fence posts. I think my Wacom tablet is going out. Okay. So I've got n plus 1 fence posts, but I have n meshes, and that would be 5 meshes. You can use other schemes. It's just good to try to be consistent. It also helps when you give your computer codes to someone if you've been consistent throughout. I want to talk a little bit more about why using such a notation is important. Here we're doing one-dimensional problems. When you get into your engineering courses, you're going to end up doing 2- and 3-dimensional problems. This is what I have done in the past, and it's worked pretty well. Let this be the x-axis, and this is, say, the y-axis, and let my object be sitting here. Example like that. Well, now I'm going to have to mesh. I'll have to mesh it in 2 dimensions, and I have to mesh it like this. So here's my very crude mesh in y. And now let me make a mesh in x. Now each little point has to be determined, each little square here has to be determined both an x and a y mesh, some kind of identifier. So what I use for the x-axis, I can use capital N for the, I need a pen, capital N for the number of meshes in the x direction and little n for the mesh counter in the x direction. In the y direction, I can use capital M for the number of meshes in the y direction and little m for the counter. So I've tagged these two together by using the same letter of the alphabet, just upper and lower case. Like I say, the book does something different. I think this works out pretty well. Okay, so that's it for the preliminaries. The rest of the lectures will be on the different types of numerical integration and on their errors.